Momentum is one of those important things in physics that everyone should know about. Unfortunately, one of your best sources for learning about momentum is in a physics textbook, and physics textbooks are drab and generally suck. So we figured we'd make a video explaining those concepts. The initial thing you need to know about is that momentum is an object equal its mass times its velocity. Knowing this, we can learn not only that momentum is conserved in a closed system, but we can also find out how outside influences or impulses affect the momentum of a closed system.
Alright, so if we have two objects, object A and object B, we can say that the force of B acting on A is equal to the mass of A times the acceleration of A. And that's equal to the opposite force of A acting on B because of Newton's third law. So then taking these two parts of the equation, we can just say mass of A times the acceleration of A is equal to the mass of B times the acceleration of B. Now, if we have the equation for acceleration, we can substitute the change in velocity over change in time for acceleration. And since the change in times are equal, we can multiply them and take them out of the equation, which then gives us the mass of A times the change in velocity of A is equal to the mass of B times the change in velocity of B. And up here, we have the momentum equation, which is P equals M times V. So this gives us the change in momentum of A is equal to the opposite of the change in momentum of B, which is the momentum form of Newton's third law.
So from there, we can break this equation down into the mass of A times the final velocity of A minus the mass of A times the initial velocity of A is equal to the opposite of the mass of B times the final velocity of B minus the mass of B times the initial velocity of B, which then can be simplified into the momentum of A minus the initial momentum of A is equal to the opposite of the momentum of B minus the initial momentum of B. We can then distribute the negative to get the momentum of A minus the initial momentum of A is equal to the opposite of the momentum of B plus the initial momentum of B. From there, we can swap this stuff around. We get the momentum of B plus the momentum of A is equal to the initial momentum of A plus the initial momentum of B. From there, we can determine that the momentum is equal to the initial momentum, which is the law of conservation of momentum. Yeah, thank you. Woo!
Now that we understand how the equation is derived, let's see it in action. Take these two fools running into each other. They both weigh about 80 kg and are moving at 2 meters per second on an essentially frictionless surface. As you see, when they run into each other, they bounce back and are now moving 2 meters per second in the opposite direction of where they once ran. This is a law of conservation of momentum in action. Let's go to a lab demonstration of the conservation of momentum now. When these two cars are running onto each other on this frictionless flat surface, the sum of the momentums of two cars initially times the sum of the momentums of the two cars after the collision should be equal to each other. As you can see by the data we collected and by this graph, where initial momentum is plotted along the x-axis and final momentum is plotted along the y-axis, the idea of the conservation of momentum is essentially backed up.
So we start off with the average force net is equal to mass times average acceleration. We can then break down average acceleration into change in velocity for change in time. So the average net force is equal to mass times change in velocity over change in time. We can then multiply both sides by change in time to get average force net times change in time is equal to mass times change in velocity. And over here we can see that mass times velocity is the momentum. So mass times change in velocity is the change in momentum. So we have force, the average force net times change in time is equal to the change in momentum. Then we have average net force times change in time is also equal to the impulse. So the impulse is then equal to the change in momentum, which is then the impulse momentum theorem.
Now that we understand how the equation for impulse is derived, let's see it in action. As you can see, my buddy slapped me across the face. The initial momentum on my face was 0 as my velocity was 0. But after being slapped, my momentum became non-zero. The force of the hand slapping me across my face provided an impulse, changing the momentum of my face. If the slap were to happen at the same force but faster, my face would have had less of a momentum after the slap, as the time component of the impulse formula would have been lowered. Let's demonstrate this in the lab. As you can see, one car is being rammed into a force probe on a frictionless surface. The car's initial momentum clearly differs from a car's momentum after the impact. As a car is moving in the opposite direction, the impulse of the collision with the force probe is causing this. If we look at the data and graph, which has a change in velocity plotted on the x-axis and the impulse measured by the force probe on the y-axis, the idea of impulse being the impulse force time length of time is experimentally backed up, as the slope is equal to the mass of the car. We hope you learned something about momentum and weren't bored out of your mind. To recap, momentum is the velocity times mass of an object. In a closed system, momentum is conserved and the impulse is the change in momentum, which is equal to the impulse force times the time of collision. Thank you guys.
My name's Gerald. I am teaching about physics.